Perfect. Okay, so I'm going to speak about this module space of quantum toric varieties. This we first defined this space in this paper from 2021 called Quantum Non-Commutative Toric Geometry Foundations. So that's from 2021. And again, the basic idea is that one would like to have this modular space of toric objects, toric spaces. I feel tempted to say toric varieties, but of course one has to be very a little bit more careful as to what one means by variety, I suppose. But in any case, it's a generalization of the basic object of this model space is a generalization of the concept of toric variety, in that the most basic property that is being generalized is that the fan or the polytope that defines the toric space needs no longer be rational. Now it can be an irrational object. It can have, if you imagine that it is a fan, now the rays can have irrational directions. And that's the main property that is being generalized. And again, in classical toric geometry, we have a torus, and this torus is being compactified or partially compactified to define one of these toric objects. And that was the thing. But to define a modular space, we are forced to consider more general tori, if you may, that still are partially or totally compactified. So in the past, there is only one, so to speak, abelian group in the world, that is the C star cross C star cross C star cross C star. But now this necessity of defining a modular space will introduce more tori. And again, we just partially compactify or compactify this tori to form the various toric varieties or toric manifolds. And traditionally, convexity and rationality are conditions that arise naturally in classical toric geometry. This is more or less a picture of the moment map, and in the simplest examples, or in the projective case, we have these rays that are perpendicular to the faces of the polytope, and they are of rational directions. And now we want to consider what happens when the directions are non-rational. We're forced to consider what happens when the directions are not rational. This is all the classical story. Quantum toric geometry then is the art of replacing the classical tori by quantum tori. Some people call it the non-commutative torus, but it's slightly confusing because we want to insist that these are or rather, because it starts to be a little bit too categorical rather than categorical, the story, Picard stacks. But what this more intuitively means is that they remain to be these abelian group objects, and then this new tori, a lot of tori that we want to compactify. And this is a deformation of the classical toric geometry, and it will provide also the basis for a deformation of the classical tropical geometry. So is of a piece with tropical geometry. This can be made more and more literal depending on which foundations you are willing to deal with. If you think of a toric variety as defined by its algebra of regular functions, then indeed a quantum toric variety or space will have a non-commutative algebra of regular functions that will be a deformation of the for example, if you just consider a cone and you consider the algebra that he is given by these monomials and so on, this indeed will be a von Neumann algebra deforming the algebra of the cone. This is the simplest example. Of course, the complication arises in that you want to glue these cones, or you want to glue these algebras. You don't glue them literally. Categorical situation because of the Morita equivalence that could arise when you try to glue the various algebras. Anyway, in the classical case, you have rational cones, and you have these algebras that come from these commutative semigroups. And in the quantum case, you will deform these algebras into von Neumann algebras with a parameter h bar. That rather than being like in the classical quantum mechanics, h bar just one-dimensional parameter, it could be a multidimensional parameter, depending very much on the dimension of the toric variety. And of course, rather than having affine schemes, then you will have something else. And this U sigma that you had in the classical theory will become will become a stack. But not only will become a stack, it will become a very non-separated stack. That will not be algebraic by any means, because it will need the addition of the exponential function in its definition, but will live in this world of all minimal geometry and so on and so forth. So it can you can still use a lot of these tools from logic and etc. Well, these are examples, very elementary examples. And of course, I already mentioned that there is a polytopic case that is especially nice for convex bodies that will connect with the study of the moduli of convex bodies sooner or later. But the basic building block of the theory, again, is the non-commutative torus, or the quantum torus, rather. And I already mentioned last time, so I will say very quickly that what most people think, let me use the pen perhaps here, laser pointer here. What most people think of the non-commutative torus, or the quantum torus, is they think of it as an algebra. It's slightly, frankly not horribly, non-commutative algebra. It has two generators, and then they don't quite commute, but when you try to commute them, this factor appears. For us, in this theory, in this modular space, will be important that H bar is a real parameter. The general quantum torus, typically H bar is a complex parameter. And that's another very interesting story that I won't tell today. But for us, it will be a real parameter, and the algebra can be realized as an operator algebra. And this operator algebra is appear first, very famously and very importantly, in quantum mechanics. And when we make H bar tend to 0, the typical situation in the process of dequantization, where this complex thing disappears, then you get just a commutative algebra. So the quantum torus becomes just the ordinary torus. This, nevertheless, is a little bit more confusing than one would think, because as H bar has the manifestation of an extremely important dichotomy for our theory, that is whether H bar is rational or irrational. Just to get ahead of myself, when H bar is rational, this algebra is essentially commutative. And when H bar is irrational, this algebra is essentially a non-commutative algebra. But of course, as you vary H bar, now you can see that you jump from quotation commutativity to non-commutativity all the time. So, and this is what I was saying, is truly non-commutative only if and only if H is irrational. And the technical term is that when H is rational, the algebra functions is, this algebra is Morita equivalent to the commutative algebra xy equals yx. Where, again, this Morita equivalence is an additional complication that makes the situation slightly too categorical. In any case, it will be very helpful and will be just the right thing to do to go back to geometry and think of. So far, we have been motivated by, it's an algebra of operators. This algebra of that can be realized as an algebra of operators, and an algebra that certainly C-star algebra, and this arises in quantum mechanics because we're thinking of non-commutativities. But we may want to abandon the non-commutative way of thinking that has all the problem of all these Morita equivalences that makes the gluings hard to guess, because now the gluings are just not identifications, but are modules. They are isomorphisms, so they are modules, left-right modules of different algebras, and this thing starts to get very complicated. So we may want to abandon for a minute this way of thinking and take a more geometric way of thinking. This was pioneered by Alan Kohn, that observed that algebra, the algebra that we just had 2 slides ago, this algebra, the algebra that we were talking about, algebra is easy to remember. This algebra arises as the of regular functions, so to speak, poetically speaking, of a space, but a space that it's really at first confusingly different from a manifold or an algebraic variety or whatever. That is the space of leaves of affiliation. So this says that it's that it's more or less to think of certain families of quantum spaces, and this is Alan Kahn's philosophy, than it is to think about certain foliations. But now, foliations, you think of these foliations in ordinary geometric commutative terms. So you get rid away of non-commutativity, and you pay with the price of thinking of foliated geometry rather than geometry. So if you're going to think of these foliated complex manifolds, and that's what we're going to do, then they may you can think they are generalizations of just complex manifolds. There are now these foliated complex manifolds extend to U category, you know. If the foliation is made of points, it's just a complex manifold, of course. And it's a bigger category of foliated complex manifolds. And moreover, you may even want to, Alan Kahn didn't go much there, but it's not too much of a dramatic step to not only think of the foliation, but think of them as parametrized leaves. So you think of them as specific dynamical systems. Of course, if the leaves of the foliation are just points, there's no dynamics to speak of, and it's just classical complex manifolds. But if the leaves are giving you these multidimensional flows inside the complex manifold, holomorphic everything, then you have a bigger category of objects. And it is an observation that starts with examples of Alan Kahn, and then it becomes a more serious thing. That studying many quantum systems is the same as to study these foliations. The way he says is the space of leaves of the foliation. Maybe I should say the modular space of leaves, where every point is a leaf of the foliation. This should be more or less the quotient of the complex manifold by this action of this dynamical system. But of course, this quotient could be rather bad. And it's already depicted in the situation at hand, where we can think of an ordinary torus. We have this ordinary torus here, but then we have a linear flow, you know, that goes just with this along this. If you unfold the torus, you take just the universal cover. In the picture, it would be R2. Then you can consider lines of a fixed slope, and this slope is going to be the h bar parameter, and then you divide by the lattice, and then you get this picture here. And this is h bar. Then the holonomy, that is how far you come back, follow a line, and then you come back to this transversal fixed chosen circle, and this is h bar. Well, this is h bar. This is h bar. This is the holonomy of the foliation, and it is an interesting fact that this foliation produces the algebra of the quantum torus. Well, this is notice that to define the foliation, I am in need of the exponential function, and this is a critical observation. This is a critical observation. Is the function that makes our theory, one, non-algebraic, but two, not too far from non-algebraic. So we have this, and once we have this foliation and its holonomy, well, we get typical things in the theory of foliations, like some groupoids associated to the foliation. In this case, in this particular case, it can be thought as a group action. You can take this transversal circle and this irrational rotation. And if you think of this transversal circle acted on by this irrational rotation that sends this point to this one, then the quotient of this circle, this acted on by this irrational rotation, should be the same as the quotient of the two-dimensional torus acted on by the this flow, this dynamical flow in the torus that is depicted in the picture. And we want that quotient to be the quantum torus associated to h bar. Again, the arithmetic dichotomy exhibits itself very nicely. If h bar is rational, this is a foliation of the real torus by circles that are PQ torus knots. But when it's irrational, each leaf winds densely inside the torus. The closure of each leaf is the whole of the torus. So it's very, 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 very different. When it's rational, the closure is nothing, it's of measure 0. When it's irrational, it's everything. And as a first approximation, we just think of this quotient in the category of topological spaces. But of course, again, if H is rational, the quotient clearly is just topologically a circle, and even geometrically. But when it is irrational, it's clearly the dividing by this action will give you a non-Hausdorff topological space, which is quite bad and looks nothing like a manifold. And I would like to study it as we study manifolds. So we have to do something being able to do that. Again, this is what I already said, that it is the same to divide the two-dimensional torus by this flow as it is to divide the transversal circle by the discrete group. Finite whenever h bar is rational, and discrete h bar is irrational, of rotation by an angle of h bar. And we get, well, this non-Hausdorff, typically this non-Hausdorff topological space. Well, the way to alleviate this story is to observe that you can think here in all the examples really at hand today, that you have here a group acting on a manifold. Be it R acting on, in fact, the examples right now is R acting on the two torus, the real classical two torus, or equivalently, this rotation, this group rotation acting on S1. And so this is the object that lives here. And there is a way to go from this to a non-commutative algebra. It's called the convolution algebra of the group action. So here we do the convolution algebra. And we can divide by some equivalence where this group action and this group action turn out to be equivalent. Essentially, it's equivalence of categories. think about it. This is a category. You can think of it as a category that has as objects the points in the torus, and as arrows a point in the torus and a time, and this is an arrow, this is a point in the torus, and then you flow that amount of time, and you put the point, and this is an arrow in a category, and this is a category. In fact, a group point in that all the arrows have inverses is another category, where you have a point in the circle, and an arrow is, well, you can think of it as this, and how many times you are going to apply the rotation, and then this is a typical arrow. So these arrows look like S1 cross Z in the irrational case, or whatever, or Z cyclic in the rational case. And these two categories, if you think of them as categories, although this one has much less objects than this one, they are equivalent categories. This is this, and we are dividing by this equivalence relation here. We're dividing by this equivalence relation called M, Morita. Here is a slightly more elaborate equivalence relation, but designed to correspond to this one, and it's made up by modules and so on. It's called the Morita equivalence. And a non-commutative space is a Morita equivalence class of a non-commutative algebra. And stack is a Morita equivalence class of this sort of global or local group actions. When the group action is only local, it's called a groupoid, much like in an orbifolds. And so you get these stacks going to non-commutative spaces. And so that's what we will do to have something that looks like a space, namely this or these, from the information, not only the algebra, that it wants to be the algebra of regular functions on this space, but now the relation is a bit more elaborate and complicated than in the classical case. We have the group action, the flow on the two torus, or the rotation on the equivalently. They land on the same equivalence class, the same stack. And this algebra, this convolution process, that if it was a group acting on a point would be exactly the convolution algebra of functions on the group. But in this case, it's this algebra that we started with, then goes to its Morita equivalence class, and this is, but well, the whole point is that it's very natural to consider this as our space. And this is the quantum torus seen as a stack. And this is important because what we will do is we will compactify in the category, we will work on the category of stacks. And we will compactify these quantum tori. These are the abelian groups in the category of stacks. And to be absolutely fair, I mean a little bit cavalier here, in that these stacks are living over the whole side of complex analytic. And I may want to restrict the sites where I'm working on, and so on and so forth. And this is done in the paper carefully. But this is what's going on. And this is, we will work as stacks. We will compactify this tori in the category of stacks to get the quantum toric stacks, and so on. So again, we have 4 avatars for the quantum torus: the group action, the foliation, the dynamical system in the torus, the non-commutative algebra, that is an operator algebra, the non-commutative space, that now we will fix names and we will call these the non-commutative torus, use the monitor equivalence class of the non-commutative algebra, and the stack, and this we will call the quantum torus, just to fix the names. So these are the 4 avatars for the quantum torus, but we will call for the quantum torus. We will call the quantum torus. And well, we have this very nice category of stacks, Now, nice thing about the category of stacks is that you can, for a lot of purposes, pretend that is the category of manifolds. And this is very nice. All I can say is that this is very nice. And now you can geometry, you can say it's a Kähler stack. Yes, the quantum torus as if I define it over C, will be a Kähler stack. And to say this for the algebra it's convoluted and hard and full with possible pitfalls. And yeah, but it's much easier for the stacks. Already the machinery is there. And well, now all these things are become rigorous statements. Here, the most important remark is that that this thing can be written a third way. This is the torus with the dynamics, the foliation. This is the circle with the radiation. But I can unfold the circle and get the numbers. But notice that now it's linearized, so to speak. So now the real numbers modulo that is in the irrational case. This is an I'm getting confused here with the irrational case. It is a thing that this group will be isomorphic to Z plus Z in the irrational case. Again, same dichotomy. So I don't know what I did. I pressed one of these buttons on the pen and now it's went insane. Okay, but it's okay. So no, I'm going in the wrong direction. Yeah, in the irrational case we have this. In the rational case, of course, this is isomorphic to Z. The same dichotomy. This is R mod Z. Well, it's just a circle in the rational case. But in a way, I like you to even think that the rational case, as it is coming into being from this point of view, is it's in a way R mod Z. So it is S1 mod Z. This is the rational case. Where Z is doing nothing. Z does nothing. And in the stacky world, S1, this is kind of an orbifold that has a Z stabilized everywhere, and it's not exactly S1. It has this additional Z action that does nothing because the two Z actions kind of align into each other. While in the irrational case, we have this Z2. So if you want to imagine it in a way, you imagine R, imagine this R, and then you imagine here Z2, and then you imagine somehow a map that we call H, that sends one generator to 1, and the other generator to H bar, and produces that it's called a quantum lattice in R. By me. But people in the quasi-crystal community call it a quasi-lattice. Maybe you want to call it a Q-lattice. And so you end up with this linearized version, where again, the exponential function is critical and makes this world in a logical world with a language that is slightly bigger than the usual language of algebraic geometry. And it is productive to think in terms of logic of this story. And you have this linearized version of it's R modulo a lattice, quantum lattice. And this is the way which will be natural for toric geometry to think about this story. So the quantum lattice is 1, h bar generated inside of R. And this is, we will call it gamma from now on, this sort of lattices. And this is the logarithmic representation of the quantum torus, R mod gamma. This can immediately be generalized to higher dimensions and the complex numbers, even other fields. But for now, let's just stay with the complex numbers. It's already interesting enough. And this is just, now you can define, if you may, and here we will be very careful with this D and D plus 1. This D plus 1 reflects the intuition. In the case D equals 1, reflects the intuition that is D2. And this D reflects the fact that D2, the one we just were working with, 1 gamma, 1 h bar, this one is the one that we were working with just a few seconds ago, will also be written like TC1 gamma because it is just R1 mod gamma, even though it is also T2 mod the flow. So it reflects that, and the notation reflects the fact that it's just R1 mod gamma. And that's a complex quantum d-dimensional too late there gamma, and now just as you imagine for rather than one-dimensional relation, when you have the could have a three-dimensional lattice, for example. For example, and you could imagine this very dense dust here. Gamma. And this is a typical situation. This is a typical situation. Z2 is inside Z2, and you can still divide Z2 by gamma. You can still do that and get a torus associated to gamma. And then the possible gammas in the world that are actually can be thought as subsets of R2, but are more insightfully thought of as maps from Z something to R2. These are more, it's more insightful to think of the H. And why would I think of H? You know, traditionally Planck's constant was a number. And now I'm thinking of Planck's constant as a map. But you see, this map, as I rotate, imagine that I rotate this lattice, this three-dimensional lattice, I just rotate it, move it, and this is a shadow, I'm just projecting. This shadow on the plane, you know, this is the plane, and this is some light coming into the plane. It's easy to deform the deformation parameter. It's easy to deform H. So this is the natural, a map is a very natural deformation parameter rather than just the numbers. So that's why we'll choose to think of the map. Well, what is quantum P1? Let's try to think of quantum P1, and this is already a very interesting example that has all sorts of very fascinating geometrical implications that I won't cover today, but I will start to insinuate. So the simple example of a toric variety is the Riemann sphere. And this, as a toric variety, it's important that it has two distinguished points, the North Pole and the South Pole. For the true Riemann sphere, non-toric Riemann sphere, you see the North Pole and South Pole can move because you have all these conformal mappings there. And that's what you mean by the Riemann sphere. So this is the toric Riemann sphere. Now you can't quite move these points. You know, the North and South Pole are there, and you have the torus action, C star. And there is an analogous statement for the quantum projective line. There is this quantum torus that we've been talking about. Remember, this is T2. This is also T2 C gamma. This gamma. So you got this T2, but see why it's important to put these ones down there, because this really is part, even it's T2, even cohomologically even, and I should have said that, in whichever reasonable measure of cohomology of T2, maybe Hochschild homology, periodic cyclic homology, or other versions of cohomology, whatever algorithmic version of cohomology you're using for these spaces, in whichever reasonable version of cohomology for this space, this looks like a two-dimensional space, not like a one-dimensional space. Nevertheless, it's a natural thing to form the one-dimensional complex projective space. And this, when we were developing the theory, was one of the hurdles to psychologically overcome. But it's very natural once you see it. In any case, there it is. You have this thing, the quantum toric, and then you compactify it, adding 2 points. So, how do we do this? Well, we will construct just like you constructed traditionally the Riemann sphere with 2 charts and stereographic projections. Here you do the same. So what you do is, remember these, remember T2 if you want, or C, comma, gamma equals, by definition, to C gamma equals by x E x pop gamma. And the expression here is this expression here. So this space here is this one here. This space here, well, is the same. But of course, it's hard. But here it's not so hard to see, thanks to the exponential map, that this is inside this stack. Just by adding, this is precisely adding these points 0 and infinity. I added the 0 and I added the other 0 to the two charts. That I don't know how to even draw it, you know. Pictures start to be very hard, but you can imagine something like that. And then the other one is something. This one is this one, and this one, and the other one is this. And this is, you added 1 0, you added the other 0, and you can imagine that they are like these cones of angle, well, infinitely thin angle. Anyway, CP1 is the compactification of T2CH, and you may want to imaginatively think that the fundamental group of this quantum torus is gamma, just like Z used to be the fundamental group of C star. But then there is something that is very, very, very confusing. Exactly not when it's irrational, but when it's rational. Because here you will get, for C star, if you just look at C star, you will get Z plus Z. But we know that the fundamental group of C star is plus Z. But this is because C star mod Z with Z doing nothing. So this is Stachy-wise is C star cross VZ, and this is homotopy equivalent as stacks to S1 cross S1. And so the homotopy groups are correct. So you have to remember this Z that is doing nothing. So again, the naive dimension seems to be 1. This is the naive dimension, but the homotopical dimension is 2. And the same happens for CP1. The naive dimension will be 1, but the homotopical dimension will be 2. And what is going on is even CP1 will have this homotopical dimension of 2. So when H is equal to 0, this is an interesting story. When H is equal to 0, CP1 0 is not exactly equal to CP1. If you forget this additional information, you get CP1. but this is a gerv. So what is it? I will say what it is. More or less is CP1 with Z acting doing nothing on CP1. So Z does nothing. Well, not exactly. Because it a twisted way that comes exactly from the Hopf vibration. This is exactly the two sphere. And the Z way, the way in which Z does nothing here is locally doing nothing, but globally is doing nothing as in the Hopf vibration. So what is going on? There is this absolutely fundamental complex manifold that in the case of CP1 is the Hopf surface, but it's got given by CP1. So CP1 delivers you the Hopf surface M in a functorial manner. But not only it delivers you the Hopf surface, it delivers you the Hopf surface together with a foliation or a flow that above, remember CP1 curly, CP1 curly contains the quantum torus, and this foliation here statically, holomorphically coming on N extends the Kronecker foliation. The Kronecker foliation. So inside here is the Kronecker foliation. And then it extends it holomorphically to all of N. So this foliation is the foliation that extends the Kronecker foliation. And it contains the Kronecker foliation. It contains N is a compact manifold that contains C star cross C star. And this foliation contains the Kronecker foliation, but this is more complex manifold, and this is a holomorphic foliation, extending the Kronecker foliation. And this is CP1. And topologically is S1 cross S3. This Hopf surface is complex, but non-Kähler, non-algebraic, non-symplectic. It is a complex manifold. S1 cross S3 is a complex manifold, but it cannot possibly be algebraic or symplectic or Kähler for trivial reasons, all sorts of reasons. You can check the Hodge diamond, you can check that there is no two form to be the symplectic form, and in the irrational case, all the leaps of the foliation in N, in S1 cross S3. Now, notice that S1 cross S3 contains C star cross C star. So think about it. S1 cross S3 contains C star. And this has the Kronecker foliation and ending the Kronecker foliation. But S1 cross S3, you are forced to go to a non-algebraic manifold, but in the language that in like manifold, language that contains the exponential symbol. And now, of course, CP1 is really the stack of Hopf surface divided by this C, winding around Kronecker-wise, and then interestingly at the poles. And this C winding around, all over the place in dense leaves, and then interestingly at the poles, explains that, well, the ninth dimension is the dimension of S1 cross S3 minus the dimension of C. That would be 4 minus 2 real dimensions. 4 minus 1, 3, 4 minus 1, 3, 2 complex dimensions minus 1, it could be a 1 complex dimension, naively. But homotopically, C is contractible. So CP1 homotopically will have 2 complex dimensions, 4 real dimensions. And this is the story for CP1. And let me just go a little further down. And just mention that for the toric manifold Pm minus 1, Pn minus 1, cross Pm minus 1, there is the analogous story, and it was discovered by Calabi and Ekman. And here in the P1 case, that is very archetypical, notice that S1 cross S3, the N S3, goes on top of P1, that is S2. Of course, the fiber is, and that's what I was saying about this Z here. Here is the Hopf vibration, the Hopf vibration, so it goes S1 versus 1. But really, it does it by elliptic curves, elliptic vibration. And in fact, there is a trivial elliptic vibration given across P1, P. And to this, is missing the theory of the log transform. What is missing to create this quantum toric theory is the foliation. The extending the Kronecker foliation is what is missing in the theory of the log transform. But you can do it, and you can extend the Kronecker foliation. And then you obtain this story, the whole story for P1. And it depends which Kronecker foliation did I extend. Which Kronecker foliation did I extend? This is also the way to produce the modular space of quantum P1s as I vary the slope of the Kronecker foliations that I am compactifying in the complex geometry that is non-algebraic. And it's algebraic because the log transform instruction sends you into the algebraic realm. Kodaira's log transform. And all this has a classical story observed by Calabi and Ekman, where you generalize this log transform story. And moreover,
I would need to go in 10 minutes.
Yeah. Let me just say this last sentence. And moreover, you could also have this story for and you have this. You can.
Sorry, you should repeat the last sentence. You are disappearing.
Also, sorry, that this generalizes not only to P1 and not only to Pn minus 1 cross Pn minus 1. This generalizes to an arbitrary projective toric variety. It's non-algebraic, non-Kähler, non-symplectic, an affiliation that does the job. But I'll come back to this next time. This is a very nice place to stop.
Thank you so much. So one question I didn't quite understand how you make this inclusion of C star cross C star to S1 cross S3, like you had it on the previous slide.
Yeah. Well, yeah. It's so hard. This one here. Well, think about it. Of course, this S1 is one here. And here you have an S1 that will be this S1. And you just need 2 more copies of R, don't you? That are on this S3.
Yes, that's right.
So you can, So you can erase enough things on S3 to obtain C star cross C star. The interesting part is that it lives there as a complex submanifold that is now algebraic and Kähler and everything. But when you compactify it to the Hopf surface, it's no longer algebraic or anything like that.
That's quite astonishing. Yes.
Yeah. So it's a very interesting story. It's a very interesting story, the whole story.
Thank you so much. Okay, stop recording.
And here we're into the convex bodies and all that. And it will dovetail with your story.
Okay. Great.
Very well.
Thank you.